Today, we're on a journey. We're going to take a simple, straight line and, step by step, transform it into a seriously powerful tool for making accurate predictions. It's all about building a better model. And we're going to start with a real-world puzzle. Okay, so let's get our hands dirty with a real problem. You know those low-cost air quality sensors you can buy and install yourself? They're everywhere. But here's the thing. How do their readings actually stack up against the super accurate official government sensors? That's the big question we're tackling today.
And, well, here's the catch. They don't really match up. It turns out the low-cost sensors almost always report higher pollution levels than the official ones. So, our mission is to build a model that can figure out exactly how to correct for that difference.
So, how are we going to get there? We've got a 5-step game plan. First, we'll start with a simple line. Then we'll get into crafting better features. After that, we'll face the big bad wolf of modeling, complexity. Then we'll learn a really slick trick to force simplicity. It's called regularization. And finally, we'll put it all together for smarter models and, you guessed it, better answers.
All right, let's kick things off with the most basic tool we've got, a simple straight line. This is going to be our starting point, our foundation for figuring out what's going on between these two sensors. So, a simple linear model, it pretty much does what it says on the tin. It just draws the best possible straight line to show the relationship between two things. For us, the outcome, the thing we're trying to predict, is the reading from that low-cost sensor. And the explanatory feature, our clue, if you will, is the reading from the official sensor. And what happens when we feed our air quality data into this model? Bam! It spits out a line with a slope of 2.1. Now, what does that actually mean? It means for every single unit the official sensor goes up, our little low-cost sensor jumps up by 2.1. So yeah, basically, it's reading about twice as high, consistently. Okay, so our first attempt gives us an average error of about 2.8 parts per million. Let's just call that our starting score, our baseline. It's not terrible, but you know the question's coming, right? Can we do better? Oh, you bet we can. And that brings us to our very first upgrade. Crafting better features. We're about to give our models some more intel to work with, and hopefully that'll help it make way smarter predictions. You know, the scientists looking at these sensors had a hunch that maybe other stuff was affecting the readings, like the weather. So, what if we throw another variable into the mix? Let's try adding relative humidity. Just like that, our simple line model evolves into something new, a multiple linear model.
And this right here introduces a really, really important idea in machine learning. I love this quote because it's so true. Building a great model isn't just about having the data, it's about how you prep the ingredients, you know? This whole preparation process actually has a name, feature engineering. Think of it as the art, and sometimes the science, of taking raw data and shaping it into features that really help the model see what's going on. Now, inside this world of feature engineering, you've got two main approaches. There's feature selection. That's like going through your pantry and picking out only your best, most flavorful spices. Then there's feature extraction. That's more like taking a few of those spices, grinding them up, and creating a totally new, super potent spice blend. One picks from what you have, the other creates something new. So, did it work? Heck yeah, it did. Just by adding that one new feature, humidity, our model's error plummeted from 2.8 down to 1.8 parts per million. That is a 35% improvement in accuracy, all from a little bit of clever feature engineering. Okay, but here's where things get tricky. As our models get smarter and more powerful, a new danger sneaks in. We added one feature, and it was great. But what happens if we add too many? This is where we run into the problem of complexity. Just take a look at these two graphs. On the left, you see that green line? It does a pretty good job of capturing the general vibe of the data. That's a good fit. But now look at the one on the right. That line is going crazy, wiggling all over the place just to hit every single dot. It hasn't learned the pattern at all. It's just memorized the random noise. And that is a classic case of what we call overfitting. Think of overfitting like this. It's like a student who doesn't study for a test. They just memorize the answer key to the practice exam. Sure, they'll get 100% on the practice test, but the second you give them a real exam with slightly different questions, they're going to bomb it. They didn't learn the concepts, and that's what we need from our model. It has to learn, not just memorize. And this gets to a really critical point. The goal here is not to build a perfect model that can explain every tiny random fluctuation in our data. The legendary statistician George Box put it perfectly. All models are wrong, but some are useful.
We're just trying to build a useful model, one that actually works in the real world.
So, how do we fight this urge to get too complex? How do we make sure our models stay useful? Well, luckily there's a solution, and it's an elegant technique for forcing simplicity called regularization.
Here's how regularization works. It basically adds a penalty every time the model gets more complex. Now, the two most popular ways to do this are called ridge and lasso. You can think of ridge as being kind of a gentle coach. It nudges all the features to have a little less impact. Lasso, on the other hand, is a strict editor. It will straight up delete the least important features by forcing their impact down to absolute zero. This picture is actually a brilliant way to understand why lasso can just get rid of features. So the best answer is wherever those red ovals first touch the blue shape. For ridge, that blue shape is a smooth circle, so they could touch anywhere. But look at lasso's shape. It's a diamond with sharp corners. That means it's way more likely that the first point of contact is going to be right on one of those corners. And what happens at the corner? Well, one of the features has a value of exactly 0. Boom, gone. And here you can see it in action. On the left side of the plot, the penalty's low and lots of features are doing something. But watch what happens as we move to the right and increase that penalty. You see the lines getting yanked downwards until they hit 0, one by one. That is automatic feature selection right there. It's an incredibly powerful way to clean house and simplify a complex model. Wow, we have really come a long way, haven't we? We started with just a simple line. We learned how to craft new features. We figured out how to tame complexity. So now, let's put all the pieces together and see how these tools really do give us smarter models and way better answers. This table is a great little cheat sheet for the main ways to pick the best features. And you can see there's a clear trade-off, right? Filter methods are super fast, but maybe a little basic. Wrapper methods are incredibly thorough, but man, they can be slow. And then you have embedded methods, like that lasso trick we just saw, which kind of give you a powerful sweet spot right in the middle. And that's where our journey wraps up. What we've really seen is that building a fantastic model isn't just about having the fanciest algorithm. So much of it comes down to the creative, clever process of feature engineering. At the end of the day, our models are only as good as the features we give them. And that leaves us with a really big question to ponder. What's the next feature out there, just waiting to be discovered, that's going to completely change how we see the world?